exact solution of the Cox-Ingersal model. So for this one, we are going to say, first we can remove the brackets. So we are going to get dRt is equal to alpha mu minus alpha rt dt plus sigma square root of rt dwt. So for this one is as rt. So we are going to use this one. So to find the exact solution, dRt is equal to negative alpha rt dt. You can think divided by rt. Then we integrate both sides. So we are going to get natural log of rt is equal to, this one will go with that one, get negative alpha t, because when we integrate dt you get t. So we have to find, for it to look like it was lemma, we have to introduce a constant here. So we get natural log, but before we introduce constant, we have to remove the natural log for rt to be constant. So we are going to use exponential sort. We are going to get rt is equal to exponential raised to alpha t. So we have to introduce the constant here. We get rt, which is equal to f t rt, then exponential raised to alpha t. So we make this one to be subject. So we get f t rt is equal to rt exponential raised to alpha t. Then from this point, in order to find the exact solution, we have to use the Ito's lemma. So we use Ito's lemma. Ito's lemma, which says that change in f over change in t dt plus change in f over change in, we use rt dRt plus a half second derivative of that one dRt. This one should be squared. So we are going to use this one to solve this one. So first we are going to see change in f over change in t dt, which is equal to, this one is as t. So you get alpha, when we differentiate alpha rt exponential raised to that one. Second, we come here, we have done with this part, change in f over change in rt dRt, which is equal to this. We differentiate this part, we get change in, we get exponential raised to alpha t. Then second derivative, this squared, which is equal to, just it as rt, so this one becomes 0. So from this point, we are going to substitute from with this equation of Ito's lemma. Then we integrate from 0 to t. So this one we integrate from 0 to t. We get from 0 to capital T dRt exponential raised to that one, which is equal to, we integrate this part from 0 to t alpha rt exponential raised to that one dt plus, we integrate this part from 0 to capital T exponential raised to t dRt. But remember our dRt is equal to this part. all of it. So that means from this point, we can use the point, we say changing RT exponential raised to alpha t dt, then plus this point exponential raised to alpha t dRT. So we have dRT is equal to this point part. So you can say changing RT exponential raised to dt plus exponential raised to alpha t in the bracket, get alpha mu dt minus alpha RT dt minus sigma square root of RT TWT. So when we open this one, we are going to get alpha RT exponential raised to dt plus alpha mu exponential raised to alpha t dt minus alpha RT exponential raised to alpha t dt minus sigma square root of RT exponential raised to RT TWT. So, but we can see that this part is the same as this one. This one is positive, negative. So this one we can go. So we will remain with that part and that part. So means that we are going to integrate from 0 to t d, then RT exponential raised to alpha t dt, which is equal to, we integrate this part from 0 to t alpha mu exponential raised to minus, we integrate from 0 to t this part sigma square root of RT exponential raised to WT. So for this one we will cancel out. So we get R capital T exponential raised to alpha capital T minus R naught is equal to, this one will drop, we cancel with this one when we integrate. So we get mu with the bracket. So this one will drop here, cancel with that one, we get mu from t to 0. So here we are going to get exponential raised to capital T minus, this one becomes 0, this one will become 1, minus sigma square root of RT integrate from 0 to t, then exponential raised to t dWt. Because this one is a white noise, you can't integrate the white noise, but you can remove this one because they are constant. From this one we can, because we want to make RT the subject, we can take this part to be the other side is positive. So we get RT exponential, that one is equal to R naught plus mu exponential raised to that one minus 1 minus sigma square root of RT integrate from 0 to t exponential raised to then dWt. So in order to make this RT the subject, you have to divide with exponential raised to alpha t. So you get exact solution of Cox-Ingersal model. You get RT is equal to, when we divide this one, we cancel, but if we divide with this one, it becomes opposite negative. So we get R naught exponential raised to negative alpha t plus mu in the bracket exponential raised to alpha t minus alpha t becomes exponential raised to 0, which is equal to 1 minus alpha negative exponential raised to alpha negative alpha t, plus sigma square root of rt with a grade from 0 to t, then exponential raised to negative alpha. We start with capital T minus t, then dwt. This one is exact solution of Cox-Ingersal Ross model. So we have to find the, next we are going to find the expectation and then variance. So we are going to find the expectation of RT. So expectation of RT, previously we said that expectation of dwt is equal to 0. So that means this part is equal to 0. So expectation becomes, or mean of RT is equal to this one. So mean of RT or expectation is equal to Reynolds exponential raised to alpha t plus mu in the bracket 1 minus exponential raised to alpha t. So we come to variance. Variance of RT. We see the variance of constant is equal to 0. That means this one is constant, this one is constant. So it becomes 0. So we are going to concentrate ourselves with this point. So we are going to say variance of sigma square root of RT with a grade from 0 to t exponential raised to negative alpha from capital T minus t small t dwt. Then multiply by expectation of RT. So we are going to get sigma squared of sigma RT but this one is inside the bracket. So when we solve this one, you get the variance of RT. So we can continue and solve it. It's just easy. Thank you. Kindly subscribe, like and share.